My main aim today is to give you the an idea about the how to make the design spectra for the and the maximum creditable earthquake risk spectra from uh, the spectral hazard map. So that map will be available uh, with a 2% probability of accidents in 50 years and 10% probability of accidents in 50 years. The seismic hazard maps are available. And from there, if we need to calculate the design spectra for the design of the building and the structures that engineer needs to design, then how to do that. Okay, so that parameter they need to provide. Okay, or as an engineering seismologist, you have to provide that design spectra data to the engineers, and they will use that for the building constructions, right? Now, uh, now, just to have a background, is this that there is a uh, there is a constant revision of this code by the governing bodies, which are basically the American Society of Civil Engineers, ASCE. Now, ASCE is basically every 4 years they they revise, or they meet together and then decide on the code and then try to revise it, or might we keep it untouched, and then it recommend it to the National Hazard Reduction Program, NHERP. So this NIHARP accept the whatever the ASCE told to them, and then they were basically discuss it among themselves. So this is the USGS organization, US Geological Survey, and then they accept it. And after they accept it, it will be integrated to the building code of the US building code. And whenever US building code has approved it, then ultimately it is gone to the international building code. It is called IBC. So IBC in the next year, or might be next subsequent year, they adopt the things. So it comes from the US, and then gradually it has gone through the international building code. But of course, when it goes to the international building code, then what will happen that the other countries, say suppose the European countries, when their opinion, or the European Community EC, we call it as the EC8 or EC things. So European Community also provide their observations on their code, and then they had uh, the other countries also, say suppose Turkey, India, all the people have their own version, and then they adopt some part of the international building code, some part they had to modify to suit on their purpose, and then ultimately the building code of each country was being decided, right? And that is where building practice was being followed, and that is why the building was being designed for, right? So that is what we call it as a design code of the building. So now, so far, that means from since its inception, there was a very simple rule to follow the building code. But as soon as the big earthquake happens in the US, and it's in that area, so they had recognized at the time what are the deficiencies of the buildings, and based on that, they try to modify the building codes, right? So after 1994, this all our Northridge, and then after the post Northridge earthquake, and then all the things. There are substantial money revisions of the building code at the time, but after that, gradually, it was all being kept constant. But after after the 22, the 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 American Society of Civil Engineers thought that they might need to move a considerable part of things, and what they decided is this, that to categorize the building based on a risk category. So earlier the risk part, as Professor Agarwal was showing, that there is a hazard and the vulnerability gives you the risk. So how vulnerable each buildings are, based on that the risk has been calculated, and the calculation of risk is a completely different phenomena, which I will not touch upon here, because that requires a lot of other input. But the risk, if it is there, then they should categorize everything based on the risk. So this is what they have: a 4 categories, 1, 2, 3, and 4. These are the 4 risk categories, and all buildings with a other structure represent the low risk to the human life in the event of a failure. So that means even if it is broken, there is no loss of the human life and this type of thing. So then we call it as a risk category 1. Okay, so that's a risk category 1, and then we have a risk category 2 is the all buildings other than the risk category 1, 3, and 4 are the risk category 2, and the risk category 3 are the buildings and structure which substantial risk to the if it fail, then it's a substantial things of the human life loss, then it's the risk category 3, and the risk category 4 are the basically the those which are the essential facilities. As I said, that the hospital, the school buildings, these things, these are the risk category 4. So these are the risk category calculations, and that is what we have all identified. So in the calculation, whenever we try to give this the new design code, they all incorporate the. So this is the risk category part. Okay, now let me see. So till 2000, till the AC provision 716, we do not have this type of risk category calculation or the risk building calculation to be incorporated. But in the recent change of the American Society of Civil Engineers, it is done in the AC 722. So these are the risk factor has been basically introduced, and as a result, the changes are being made how to calculate the design thing. So now we are giving a category which is called AC 722 MCE-R. So this is your risk targeted the maximum creditable earthquake. MCE is maximum creditable earthquake, with the suffix R indicate it's a risk targeted mapping. Okay. So this is the case. Earlier we were not there, but currently these have been introduced. Okay, let me go to this. And also, as I said to you the last time, when Professor Agarwal was showing all the site classes, the earlier site classes was A, B, C, and D, and E. Now they have the AC 722 have recognized there are the few other seismic site classes. So basically what they have done, they had done now the hard rock is A, having a velocity greater than 1500 meter per second. That means the VS 30 or the shear wave velocity, the average 30 meter shear wave velocity is a greater than 1500 meter per second. Then there is a medium hard rock, they called it. The geologically it will be called medium hard rock. Then it will be the 900 meter per second to 1500 meter per second. That's the category which we'll call it as the medium hard rock or the site class B. Then we call it as a BC boundary or the BC site class. The BC site class is basically between 640 meter per second to 900 meter per second. So that's the BC category. And then we call it as a very dense sand or hard clay. If it is there, if that is the soil type, then we call it as a C-class soil. And C-class soil is basically 440 meter per second to 640 meter per second. That's the VS30 values. And then D-class soil is a medium dense sand or the stiff clay. And that is between the, but there is this CD, it is a dense sand and the very stiff clay. Because the earlier was a hard clay, this is the very stiff clay. So that is 300 meter per second to 440 meter per second is the dense sand or the very stiff clay. And the medium dense sand is basically site class D, and that is basically 210 meter per second to 300 meter per second. This is the D site. And then DE is the loose sand or the medium stiff clay. So clay has been categorized as a hard clay, very stiff clay, and the medium stiff clay, and then that will be equals to 150 to 200 meter per second. And then E is a loose sand, very loose sand, and the soft clay, then that is equals to less than 150 meter per second. And then if it is a F type of soil, then it needs some special considerations. So basically, if the F soil type is present, then the code says that you need to do the special design code as approved by the local bodies. So that means the local bodies means the local municipality and all these things, whatever their building practices and their things, they need to be careful on that, because as such the international body do not needs to come into this picture, because that's a really, really bad soil. So they need to give some direction if you need to build a house or build a building in a F type of soil. So there are some special considerations required. So these are the these are the soil type, whatever now the rules are. So now the NIHAR seismic site class is not A, B, C, D, E. It is all A, B, B, C, 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 D, D, and D, E, and E, right? So these are the site class category nowadays, and mostly the code will go up to DE. E also, if the E type of soil is encountered, that means has a shear average 30 meter shear velocity is less than 150 meter per second, they also need to recommend to be to be put the design very carefully. Okay, so so for E and F, we have to be careful on that, but for the rest, they have some design criteria that we can use for the seismic design part. Okay, now, so this is all what we call it as a VS30 measurement. So that means this is the shear wave velocity for the upper 30-meter shear wave velocity. Okay, next. So average shear wave velocity, what we call it as a VS30, is basically the summation over D by summation over D by VSI, right? So if you have a, say, suppose the soil with a, we are just try to calculate 30 meters, right? So let us assume there are few soil layers. So we can go and add individual soil, and then if it is a 30 meter, we go only up to 30 meters. So that means the summation of DI will be equals to 30 meters. So that will be totally, you can write it 30, right? And then divided by individual layer thickness divided by their velocity, individual layer thickness divided by its velocity, and goes up to the 30 meters. So if it is if the 30 meter falls within a one boundary, so then we have to take that much of thickness which covers the 30 meters. After that, we should not take. So that is your average 30 meter shear wave velocity. But does it make sense to you guys? If it's not, let me explain it a little bit.
EI by me, BSI. Such, why we are taking summation of EI by P? Because have a little rough, let me. No, I'm just trying to see whether you are correct or not. Because this is velocity. Velocity means distance over time. So
this is the time factor. So time means d by v, right? The time is d by v. Because this is the total distance d, and this has to be the dimension of time. So d by time has to be the velocity. So if this is your time, then this has to be d by v. Okay, so because I also sometimes confuses this one, but thank you. I have not done wrong.
VS30 is we only go for 100 meter, 100 feet depth. That's the reason all. Other than that, for VS30, we are taking only VS30. No, as I told you yesterday that then the VS30, we are talking about the VS30 because in California, as I said, again, the California data is mostly influence every part of the world because they have a most good network and they have a collection of data for a long time. So in California, it has been found out that the building shaking is mostly influenced by uppermost 30 meters. Now, you can say that by not 100 meters, there is no apparently no reason.
But since it has been found technically that in California, that the 30 meter shear wave velocities information is critical for the structure, and that is why it has been included into the code. If some way or other someday it has been found out that some regions might see that with evidence that 50 meter is much more controllable factor, then might be in someday 50 meters shear wave velocity average may be introduced in the code, but till now it is all 30 meters, right? So there is apparently no physics behind it.
Indian region, it may be changed.
India region may be changed, may be changed, but nobody has changed it because because in the international building code they also adopt the 30 meter, so they try to be same with that. But whether 30 meter is really applicable to every area or not, that's a $1 billion question, right? But the code wise, that is what they were using, because the California, they had observed it, that 30 meter part is very significant. Okay. Yes, please.
Topographic Z elevation valley. So how much would time be for like the basement place you have worked?
No, we are not considering anything flat topography. We are considering from the surface to the tip. So whatever is your topography, take it from the zero. Okay, so basically we are not talking about any flat surface or might be the geoid surface.
Then, like, I mean, if we consider the MRL handling sea level concepts, then in certain cases, we have seen some places show like the site for the MRL as the surface carrier topography. Some places again show 480 or 460, depending on the place on region of it.
Same too.
The places where I have worked, our surface Z value was like 40 to 520 if it was cloudy. And the soil thickness was also like it can go as high as like 12 meters also including that also right stuff. And then to be a painting the
Yeah, I understand your question, but as I said, that any site, if you have any site, we will
Not, let me. So any site, we will not, even if it is a topography, suppose this is the topographic things, when you have one site here and you have another site here, I always measure 30 meters from here, so that is a 30 meter from this one, and I also measure 30 meters from here, that is this part. Now whether there is a mean sea level is here or mean sea level is here, that's a different question. If it is a height is from the mean sea level, height is only 30 meters, then it will go below mean sea level. So that's a different question that I do not know what will be the answer, but it is always from the 30 meters from the surface, from the local surface. Okay, so that will not be okay. So what I was trying to say is this, that in a VS30 calculation, say suppose this is here, say suppose this is 10 meter, say let's see this is 5 meter, let's see this is your let's see this is your 25 meters, 25 meter, right? So this is the thing. So let's see, this is a 200 meter per second. Let's see, this is your 350 meter per second. This is your, say, 400 meter per second. Might be this is 600 meter per second, right? So these are all in meters. So if I try to calculate this is value, so average VS30 will be equals to, this will be the 30 meter, that's sure. So the upper one will be the 30 meters, and then this will be the 10 by d by v, right? So 10 by 200 plus 5 by 350 plus 3 by 400. So this is 10 plus 5 plus 3, so 18. And now this is 25. So I will not go to the 25, but I will go to the 12 by 600, right? So then that will be the average MCE-R velocity value. You calculate this one and put these numbers. So that means we will be taking only up to the 12 meter from here, so that becomes a 30 meter, right? So this is 12 meters. So 12 is 15, 15 plus 5, 20, 20 plus 10, 30. So that we will be using in that way. Make sense? So that's the VS30 calculations we have to do. Okay, so
What about the shear wave velocity in a centimeter? The average shear wave velocity in 30 meter. Yeah. So, and these are the actual velocity of each wave.
okay, so everything based on the 30-meter shear wave velocity. Okay, now let me tell you the main things. So earlier we have the MCE level of earthquake. MCE level of earthquake. This is the before 2022. Okay, the design code has two things. One is a MC level earthquake.
The third question, if this LC, are we going to consider PSL? So,
Yeah.
yes.
It's a PSAT. It is a MCE means it's a 2% probability of accidents in 50 years. It is what we actually tried. 2% probability
of accidents in 50 years. So that is what we were using earlier. So that is your MCE level of earthquake. Okay. Now each one we were designing based on 2-point formula. 2-point formula. We were using it. The 2-point means in the map. In the map, we were getting a short period spectral acceleration. Short period spectral acceleration, we call it as a, because the spectral acceleration is SMS. So that's the nomenclature we use, short period spectral acceleration. And we have another value is a spectral acceleration at 1 second period, at period of 1 second. Okay, so that was equals to S of M1. So these are the two periods things. Right.
So here is an starts but gun and starts M is for the money. This class will get. Okay, so that's the single things. So these two values we can read from the unit that they provide it from the map. We can get the values. Actually,
we are not getting this value from the map directly, but we can read these values from the. Let me correct it. Which is a we can read from the map, not these values. We can read from the map. Let's see, SS. Let's write it like this way. Okay, we get it like this way. S1, S of S and S of 1. Okay, so these are the short period and this part. Okay, now these are we read from the map actually, these two numbers, and then we so these values are available from 2% probability of accidents in 50 years map. So suppose if you go to a place, you first take a map of the spectral hazard map of which says the 2% probability of exceedance, 2% probability of exceedance in 50 years. So this map, it is written like this. So this is the contour values at some point, and you have a site. So you read the site latitude and longitude. Say suppose this is your site. So you read the values of the spectral acceleration map for this longitude and latitude. You can read, say suppose this is some numbers 0.16, say this is 0.12. So you can interpolate this and read these values for the short period one map at that means at short period values. And also we have a same map is available for the 1 second, for a 1 second period, and you from the contours you again read the contour values. From the contour value you read the location where you are interested in. That location you calculate the S1 value, and this is your SS value. S is actually the short period. The S means it's a 0.2 second. Okay, so there are two controlling point. One is the 1 second and other is the 0.2 second. Right? So that's the 2 points. Then if you have calculated the site class, so now you see because this only gives you these maps are developed earlier, because this is pro 1992. They are all given for the site class B, because earlier we had only the site class B as the rock, right? So these maps are developed for site class B, but you may have a site where you are trying to calculate the design. They may have a site class, say suppose C or might be D, but that will not reflect on these values, right? So that is not been given in that. So at the time the only map is available for the rock site. So that means bottom of the engineering bedrock, that is site class B. So you have to correct for the site class. So you have to correct for site class. Okay, so you have to correct for the site class. So your site class, if you are using 2% probability of this one, so then MS will be equals to some factors. I think this is for FA into SS, and SM1 equals to FB into S1. Right, so these FA and FB are the correction factor for the site class. The correction factor for the site class. For site class. So that you can use for your maximum creditable earthquake. You have a 2% probability of exceedance and calculate these numbers. Okay, so these things are given in the form of a table. So this FA and FB value for other type of soil. So that means for the B types of soil, the FA and FB are all 1.0, 1.0, because this is actually given for the B soil class. Then C and then D, they have all different numbers. So that will be used from your SS value. This number will be multiplied, and that number will give you the SMS and SM1 values. Make sense?
Sir, if
and seeing is ground motion vector acceleration from ground motion prediction equations. It is one parameter is Vs. So the values what we are using for CD type, it is already included in Vs. So no, this maps when prepared, it is not
it is, you need not to then think about the ground motion prediction equation. These maps were prepared based on the hazard calculation. So that means this has already taken care of all the hazard values, whatever in that area they like to do. So that means whenever they had, as I show you that one calculation of the site response, for the hazard, this hazard curves is like this, and when there is a 1 second and there is a the 0.2 second type of, so this is 0.2 second and this is 1 second part, or might be anything like that. And then this side, it is a rate of exceedance. This is your rate of exceedance, and this is your some numbers. Let's see, this is the value of G, right? So what we have done, we will be taking now the 2% probability of exceedance and calculate what will be the B, right? So you have already calculated the 2% probability of exceedance 0.0040 somethings, right? So that's your probability of exceedance for the 50, but a 2% probability of exceedance in 50 years will be something around this. So you read this value, go through the hazard curve of that area, and then calculate this one. And this hazard curve you have generated by seeing that this is your site, this is one fault, this might be another fault, this is your D1 distance, this is your D2 distance, and you have calculated this curve based on that thing. So if this curve was generated, and then you have calculated that, okay, if this is my rate of exceedance, then at that time what will be the value of G, and that value is basically written here. Okay, so that's your values, but that value is only assuming your site is the Pro 1992, Pro 2022 is only using that equation for calculation of this one. Okay. Let me see this. There are the numbers. I have to see the numbers quickly. Okay, so okay, so after you calculate this SMS and SM1, we also calculate the T0. So this is your T0 values. So T0 will be equals to SM1. So whatever you have calculated SM1 divided by SMS. Okay, so that ratio you calculate, and that will be given as a, that will be calculated as a this multiplied with a 0.2, that will be equals to the T0, and this will be equals to this ratio, we call it as a TS. So TS will be into 0.2 will be equals to the T0 values. Okay, so that you can calculate with these numbers, right? So you know these values, and then what we will be doing it here, that we will try to calculate the spectral acceleration of, this is the period, time period. So this is the period value, and this is the S value. So this is the spectral acceleration at any things. Okay, now, so this is the T0, and so this is what SMS and SMN1. So now we had got this T0 value, then we have to get this TS value. So we calculate, this is the TS value, and then we have 1 second, and then we have a TL values. So this is the TL. Okay, so so these are the three part, and that we need to use. Okay, now this is what I was trying to tell you earlier, that this is your FA and FB. This FA and FB are for the different site. So if your the spectral acceleration, sorry, let's go to this side little bit. So if your spectral acceleration SS, whatever you read from the map, so you read the SS value from the map, right? And if your SS value from the map is say any value, which is the less than 0.25 G, or might be the 0.5, might be the 0.75, might be 1.0, might be greater than 1.5, then you also see your site class, because you have seen your site class. So from the site class, you know that whatever your site class is, so it is your ABCDE. So let's see, your site class is C, and you have seen your spectral acceleration SS value, which you read from the map, is say around, or it is say greater than 1.5. Okay, let's see that the spectral acceleration you read from the short period is 1.5 greater. So then you can see this C and then multiplied it with a 1.2. So that means this number will be 1.5 multiplied by 1.2. Does it make sense? If it is a less than this one, if the spectral acceleration, whatever you read, it's a 0.25, then you multiply it with a 1.3. Right? So that is your multiplication factor for the short period one. SS means short period, so that means 0.2 second. Then as per your spectral acceleration values, whatever you read from the map, you can see these numbers and multiplied it to correct it for a SMS. Okay, for the site correction. And then you have to also take the long period values, which is equals to FB. If it is FB, then also you can use the same numbers. They also give you the FB parameters. So that will be equals to FB into S1. So you read the S1 value and check in which category you value, if it is a 0.1, 0.2, 0.3, 0.4. Now suppose if you say 0.35, then also it is the 0.8, right? So basically the value will not change that much. So, but if it is a change, then you can interpolate between these two numbers, right? So that's your decision based on your SS and SD value. Is it clear? So that is your SMS you can calculate. Okay. Just a minute. So after you do that, Then you can also calculate this 0.2 and this one. Now, you can take our design spectra as DS, it is called design level, and this is called SDN, SD1. So it is this is your MCQ spectra, I mean MC spectra, and this is your design spectra. So this is what we call it as a design spectra. This is a little bit less than your SMS and SM1. So this is your 2/3. Sorry. This is your 2/3 of SMS. So you can see here 11.3. This is your 2/3 of SMS, and this is your 2/3 of SD1. Right. So these are the design level. Whenever you put the you design the code, then that design code will be take the SDS value, and that unless and until you are doing a very 2% probability of accidents type of constructions, for example, hospital and other things, so then you can do it like this way. Okay. Now, main equation for calculating the SA in between the other numbers. So you have already calculated T0 and TS and 1 and TL, right? So SA, so this spectral acceleration SA or anything, or you can call it as A, or you can call it as the SA. So SA will be equals to your whatever your SDS value and multiplied by 0.4 plus 0.6 T by T0. So you know that T0 value, you already know your T0 value. So T0 value will be equals to some numbers, and then at T equals to 0, if the T is equals to 0, then the SDS multiplied by 0.4 is equals to your SA. So this will be the 0.4 SDS, 0.4 SDS value, and then we will be draw a SDS value. So whatever your SDS comes out, you draw it here, and this equation is a straight line equation. So you can go up to this much, this line, and you just draw it like this way. Okay, so that means this is your SDS level. So you just draw this line. Graph is not
showing. Sorry. Okay, let me show you this graph there. So it will be going to the SDS level, and this is your SDS point. This is the equation.
So SA will be equals to 0.4 SDS, right? If T equals to 0, if I put T equals to 0, that means at T equals to 0 value, the SD1, this point will be equals to 0.4 of SDS. Is it not? Is it clear? So that is 0.4 of SDS because T equals to 0. And between T to T0, this equation is a straight line, right? This is a straight line equation. So it will be going up to this much. It will be going from 0.4, this one, to SDS by a straight line joining this one. And then this is your SDS value. That is what I had already plotted. And it will continue to go a straight line till your TS, and TS I had already calculated as MS by MS values, SM1 by SMS value, that I have already calculated. So that will be the same thing as SD1 by SDS, because these are divided by the same thing. So if you can divide it, it will be the same number. So therefore that doesn't matter. So it will go up to SDS, all the values to be straight line, right? After that, I also plot a SD1 value, which I have got, right? So this is what we had got it here. So just draw the straight line from the SD1 value, whatever you got, and this is the point with a 1.0. So pull this point, and this curve now I need to draw. So this curve I need to draw. So this will be equals to whatever your SD1 divided by T, right? So SD1 divided by T is basically from TS to 1.0. So at T equals to 1.0, SA will be equals to SD1. That make, so basically T equals to 1, then is this, but T equals to less than 1, then this will be equals to the SDS, right? Okay, so these are the two values, and the last value is the, we also need to calculate is the basically the TL value. So TL value we need to calculate from the also the map. So this map also give you a long period. There will be a map which will be giving you the TL values. Okay, so from that particular site, you also read that TL values number. TL is the long period numbers for the thing. So that will be also provided to you from the map. So you take the TL map and put this vertical line, and then you continue this one with the same thing, because this is the same equation from the TS to TL, and that equation we will be going on. So this will be equals to TL for the TL for the greater than T. So this will be all will be the same type of equation from TS to TL. It will be all SD1 by this. Beyond TL, it will be SA will be equals to SD1 TL by T square, right? So SA will be equals to TL over T square. So TL you have already read from the map, and this is your T value. So T is the time period, whatever you try to put these numbers. So put these things and calculate SD1 TL by T square. So you have three lines, therefore one is a straight line like this. So that will be equals to 0.4, that formula, 0.4, 0.6 T by T0. Then there is a one formula from here to here up to TL. This is equals to SDL by T, and then this will be equals to SDL TL by T square is after the TL. So TL value you read from the graph, SDS value you read from the graph. SDS you just convert it, and SD1 you also convert it, and you can follow these things to draw the design spectra of that particular place. If you try to design a building, then that building should have a design spectra like this. Okay, so and then we construct this design spectra. You can give it to the engineers, and they can put these things. Now, next afternoon, if I can do this, that then we will be doing like this way. So if I know the design spectra, so that means that is your hazard specified design spectra at that site. Okay, then we need to generate your time history, which will basically follow this design spectra. So that time history we need to generate at the surface. Synthetic time history, but whenever engineer needs to design, so his design will be checked based on the time history he has. So this is the design spectra. So our time history has to be compatible to this design spectra. So that things we need to design. So we will be using that a criteria in the NGOS2 model, and give this design spectra and try to calculate the design spectra compatible time history. Okay, and then also I will tell that what modification we have done in the AC, what is called our the new AC 722 type of model. Okay, so this is our old things. Okay, just only this one. But if we try to do it a little bit modification, what are the modifications we have done? Okay, thank you very much.